Right, so we have described the perceptron model as a decision making of this form, and now we are going to tackle how to get a good model. Previously, for our toy data sets, we just visually inspect them and we say, well, I guess this line looks good because it separates the dots, the colored dots this way. So I guess we just did one approach, visual inspection. But we certainly can't do this on real data set where you have like thousands or even millions of colored dots. So the first thing that we need to do to automatically figure out a good model is we need to come up with a some kind of measure. Well, the lingo would be an error metric, whereby so if error metric is f and I pass in my model, it would spout out a number. If it gives like very high number, like 1000, this means error is high, your model sucks. Or if it gives 0, then that means you have classified all the training points correctly, and then so you say the model is good. Alright, what would be one reasonable error metric? A popular one is called MSE, mean squared error. So before that, some illustrations. Let's see. Let's say my training set is not linearly separable, like this. Then this is an example where the cost function would return a high number. But if the data is completely linearly separable and you provided a good model, then the error function would return a low number. Mean squared error will capture this. So I will abbreviate this as MSE from now on. The MSEs, when you have been given all the x's, so I guess this should be a matrix, all the x's along with their labels, and your model, so xy are training data, would just be the average of all the classification errors, yi minus y tilde I square. Let's dissect these terms. N is number of samples, and then I is the ith sample, and we have n of them, so I goes from 1 to n. Yi is the true label or true answer to ith sample. And what's y tilde I? Well, we're measuring classification error, so y tilde I is the predicted label provided by your model, and for the perceptron model, the y tilde I is just linearity of the model's weights to that data point and the threshold. Alright, so we have defined our error metric. Then now we are going to reframe training, the task of finding good model as an optimization problem. What's an optimization problem? So if you have not seen this before, you probably have seen this from your calculus class. You're trying to find the parameter that minimizes a function, fx. Well, in this case, we are doing the same thing. We want to find the best model parameters that minimizes our cost function. But more formally, in the if f is MSE and we use the Perceptron model, then we are trying to minimize this function, whereby if we just have two dimensions in our input vectors, then our f, the MSE, is just this, which we previously wrote, yi equals wj xij plus theta equals 1 to d, the dimension. Or if you just have 2, then this is just 2. So these are the model parameters, and the right hand side are the MSE, mean squared error, over the training set. Now then, to find a good model, it's simply it's not simple. The minimizing process is tough, but it's equivalent to just finding the arcmin of W1, W2, theta of the cost function. Solving this math formulation would give you model parameters that are good, that minimizes your classification error. How do we do this? Well, so from calculus, you have learned that when you want to take when you want to find the global minimum of a function, you do things like maybe set gradient equals 0, and then solve analytically. And it turns out for the MSE and Perceptron problem, we actually do have a closed form solution. So you can Google this, ordinary least squares closed form solution, if you want to know like a one-liner for the closed form solution of this problem. But that's not what we are going to do in this class. So there are some disadvantages if we are going to do it this way. This approach is not online. That is, we assume we already have all the training samples ready, whereas an online approach would allow you to update your model whenever you receive a new sample. And then another disadvantage is that this is slow. This requires matrix inversion, which has runtime of n to the 0.3 something something. So yeah, when you're dealing with high dimensions, the closed form solution is not what people use in the industry. Instead, to solve the minimization problem, what we are going to do is gradient descent. Recap for those of you who have not seen optimization flavored problems before. This is just one of the many ways to solve arcmin of a function. Okay, let's go through an example so that we get intuition behind gradient descent. So consider z equals fxy equals x squared plus y squared. Okay, so what does this look like? If this is x, y, z, then this would look like a ball like so. And question to you is that if we start at this point, x, y equals 1, 1, which means z is 1 squared plus 1 squared is 2. And I want to get to the bottom of the bowl. I want to minimize f, right? Which direction should I go? Which direction? So I want a delta x, delta y to go to get to bottom. If you remember from your calculus class, this would actually be the negative of the gradient. So that's the direction, but we have not talked about the step size, which we will get to later. Opposite to gradient. And so let's just do the math real quick. So the gradient of f is dz dx and dz dy, which gives you 2x and 2y. And at 1, 1, what does this give you? Negative delta f is equal to negative 2, negative 2. And so you will try to move this way. So we're outside at 1, 1, and we go to negative 2, which means we are moving to the direction of the origin. That's kind of hard to see like this, so let me try again. So currently we're at 1, 1, and our negative gradient is this way, which makes sense because we are actually now approaching the origin. Now, we talked about direction, but the next question is, okay, so we talked about direction, but now, how far? How far in that direction should we go? We will use, so let's call eta be the step size, which is how far to go along that direction. And here we see why this can be tough. If eta is too big, then you would just be oscillating over and over and not be able to reach the minimum. But if eta too small, this approach would take way too long to converge. So in practice, but not what we're going to do in our homework, you can have adaptive eta, where eta would decrease over time. But in our homework, we'll just pick a fixed eta and hope for the best. Okay, so that's gradient descent, but we have one more final twist to go before you are ready to tackle the homework. Well, next week's homework. So stochastic gradient descent. We have discussed gradient descent. What the heck is this? What does this stochastic thing mean? Well, the intuition is that so gradient descent requires computing delta f, but then remember that delta f requires the entire training data. So you would need to go through all the training data to compute this gradient every time. And you need to compute the gradient many, many times because you take small steps each time. So stochastic gradient descent say, well, this is too expensive to compute. Why don't we just approximate delta f by just using one data point at a time. So let me write that down. As stochastic gradient descent says you will estimate true gradient estimated by a gradient from one sample. And now that means previously one step requires all the n data points to generate a step. Well, that's redundant. But now, with stochastic gradient, one step just requires one data point. Which means now we need to have a altered definition of the error function. We will now just define the error function per one data point to be like so. We are no longer summing across all data points. We're just taking the error for just a single data point, where while tilde is again w1 x1 plus 2x2 plus theta. So if we now are considering just this one function defined per one data point, what is our gradient? Delta f again is delta f over are the partial derivatives, and let's evaluate each one of them because this is the math that you'll be using for the homework. Yeah, so yeah, you're just doing applying chain rule to this guy, and you will end up with y minus y tilde negative x1. Sorry, I might have breezed through that. So you start with this guy, and you're differentiating this with respect to w1, and so chain rule, you take the 2 out, and then you differentiate the inside with respect to w1. And y tilde is defined like so, and the only w1 term is w1 x1, and when you differentiate that you get x1, and there's a minus here because there's a minus here. Okay, so that's one of the formulas. Similarly, we won't go through the derivation again. The partial derivative with respect to w2 is like so. And then finally, if you do the same thing but for theta, you would get this term. What does this mean? So as GD says, for each data point where you have an x vector and a label y, update model with eta times negative of the gradient. So you'd have delta 1, delta w2, delta theta, like so. y1 and this y. Okay, so these are just the gradients that we have derived above, but then we multiplied by negative eta. And then something to note is that what happens if y is the same as y tilde? Well, that means you have correctly predicted that sample, and there is no zero deltas, so no weight change, which makes sense. If you are already classifying something correctly, then there's nothing to change about your model.